We spent a bit of time just recapping basic algebra. Now let's look at the numbers themselves, some basic ideas about that. And of course we're working with the real numbers. Let's put them all together, this wonderful set of real numbers. Real numbers, so any real number can be placed on the number line. In fact, to give it its correct name, the real number line. The symbol used for real numbers, or the set of real numbers, is R, but not just R, it's what we call the hollow R. So inside the real numbers, a subset of that are the rational numbers. The symbol for rational numbers is, of course, well, we can't use R, we just used it for real numbers. So we use Q, the hollow Q, and Q stands basically for quotient, because rational numbers are, of course, any number that can be written as a fraction or a quotient. Then we have another subset, and there is no point of intersection between the two, of irrational numbers. We don't actually have a notation for irrational numbers. A way of doing it is like that. R\Q. The backslash means not including or excluding. So it's all the real numbers excluding the rational numbers. So they're either rational or they're irrational. It's one of the two. Okay. Inside our rational numbers then we have our fractions, and by fractions I'm meaning fractions that can't be simplified to be a whole number. So 3/4, 2/3, that sort of thing. Then we have integers. They're the rational numbers that can be simplified down to be a whole number. Now, the symbol for integers is not what you would think. It's not I. It's Z. Why Z? Well, it comes from German. So I think you say it as Zahlen. It's either Zahlen or Zahlen, but it's German for numbers, basically. Then we have, inside the integers, natural numbers. Natural numbers, that one has a logical one, n. And then we have a little set, it has 0 in it. What? So 0 is in that set. So natural numbers, another name for natural numbers is counting numbers. Natural numbers, counting numbers. Positive integers, that's another way of saying it as well. Okay, and then intersecting these ones, notice it doesn't intersect the natural numbers and it does not intersect 0, are our negative numbers. You can have negative fractions, you can have negative integers, and irrational numbers can be negative as well. So there's our family of real numbers that we play around with. Factors, just like in algebra we like to factorize. When it comes to actual numbers, the factors we're interested in are the prime factors, because every number, every natural number I should say, every natural number can be written as a product of its primes. For example, 324, I could break it down to be 481s, but I could keep going because they're not prime numbers. We end up with 2 squared times 3 to the power of 4. Now why, in the real world, are prime numbers so important? What's one key thing? Does anyone know? A key thing that we now deal with pretty much every day, and it all relies on prime numbers. Encryption, data security, data security. And the reason why it works so nicely is because we don't know how many prime numbers there are. We can't find them all. Right? There's an infinite number of prime numbers and their location is random along the number line. So you can't pick a pattern, so that it helps in the encryption then, because someone can't just get a computer to go, well look, every 5th number or something like that, try that, because they're just randomly, well, no, it looks like they're randomly placed. Okay, highest common factor. To find a highest common factor, rewrite both of the numbers in terms of its prime factors. We pull out the common factors. So if I wanted to find the highest common factor of 1176 and 252, I'd work out their prime factors. So there's 1176, 252, and we would pull out the common factors. It is exactly what we did with algebra. Exactly the same idea. You're pulling out what they have in common. So 2 squared times 3 times 7, which works out to be 84. So factorising, you will remove the lowest power. So when you factorise lowest power, same in algebra, same in numbers, you pull out the lowest power. Lowest common multiple, we write both numbers in terms of its prime factors, but this time we write down all the factors without repeating. And in algebra, that's similar to working out that common denominator, because that's what we do there. So 48 and 15, 48 being 2 to the power of 4 times 3, 15 being 3 times 5. And so it's just like, as I say, with the algebra, I'm going, oh, it's not there, I'm going to put it down. So 2 to the power of 4, it's not there, I put it down. 3, it's not there, I put it down. I go to the next number, 3, oh, it's there, so I'm okay. 5, I put it down, and that works out to be 240. So that's the lowest number that both 48 and 15 go into. Without cheating, so cover up your page so you can't see. Otherwise it's cheating. Who knows their divisibility test? It's useful to know that, because if you want to find whether two numbers have a common factor, it's good to know divisibility test. If you're quick, you can get the easy ones. How do you know if a number is divisible by 2? Oh, very good. It's an even number. What about 3? All the digits add to be a multiple of 3. 4. And the key on that one's the last 2 digits, and they've got to be divisible by 4. 5, anyone? 5 or a 0. What about 6? If it's an even number where the digits add to a multiple of 3, it's got to be 6. All right, here's the first really good one. 7. Here it is. You double the last digit and then you subtract it from the other digits, and if that answer is divisible by 7, then the whole number is divisible by 7. Give me a number that's divisible by 7 and we'll show that it works, and don't just say 14 or something like that. I mean, that's a bit, who's got a good number that's divisible by 7? 2786. 2786, so we're saying double the last digit. Well, that would be 12. Subtract it from the other digits. 278 minus 12. 8 minus 2 is 6. So I now have 266. Is that divisible by 7? Oh, hang on, let's do it again. 6 times 2 is 12. Subtract it from the other digits, 26. There we go. We got it down to 14. 14 is divisible by 7, so we're okay. The whole thing is divisible by 7. All right, that brings us to 8. Yeah, now it relies on the last 3 digits. 9, yeah, we're back to the sum, I guess, because 9 is 3 squared, so it's similar to the divisibility test for 3. Here comes a tough one. 10. Okay, ends in a 0. Another good one. 11. So you look at the even position digits, you look at the odd position digits, and if their sum is a multiple of 11, then we're okay. Okay, let's find one. Give me a number. 11. 10,846. Okay, so we're saying the even position digits, so that would be 0 and 4. So that's 4. The odd position digits, are those 3, so 8, 6 and 1 is 15. The difference between those two is 11. So the whole thing is divisible by 11. Okay. Did I stop? I reckon I probably stopped there because I don't think I've got enough room to put 12 in. But there are divisibility tests. You can keep going and keep going. Okay. We're talking about our numbers, and fractions and decimals. They're two different ways we could write numbers, and we need to know how to convert between the two, and most of it is pretty straightforward. This is the trickier one, I suppose. When you're looking at a recurring decimal, how can you turn that into a fraction? Because as I say, turning a fraction into a decimal, very easy. You just divide the top by the bottom and you get the decimal. If it is a terminating decimal, then again, because of the beautiful nature of our number system, very easy, because we know the first number after the decimal point is the tenths, then the hundredths, and so on. So we can work that one out. But it's these recurring ones that are interesting. Let's pick ones we know the answer to. So 0.6 repeater. 2/3, by the way, in case you were unsure. Here's a way of doing it. I know that it's 0.666, and I would just keep going, writing all the 6's down. If I let x equal that, in other words, x is 0.666 and so on, then 10x would be equal to 6.666. Simultaneous equations. Basically, I'm getting rid of that repeating bit, because that's what's causing me the problem. Once I've got definite numbers there, I can play with it. 9x is equal to 6. x is 6 on 9, which of course we know is 2/3. That's the idea. We want to get rid of the problem, the repeating bit. So if I had this one, 0.81 repeater, then I'd get 0.81, 81, 81, 81, 81, 81. So that's what I'll let x equal. This time I want to get rid of the repeating bit. Multiplying by 10 is not going to help me this time, because if I multiply by 10, I'd get 8.18, 18, 18, 18, and they're not going to cancel when I subtract. But if I multiply by 100, they line up again, and I can do that subtraction. So I get 99x is 81, x is 81 on 99, 9 goes into both of those, so we get 9 on 11. What about if not all the numbers repeat? And obviously it's the numbers at the end that have to be the ones that repeat. So the 3 is not repeating. 3, 27, 27, 27, 27. Again, I've got to get rid of the problem. I've got to get rid of that 27, 27, 27, 27. If I let x equal that, multiply by 100 so I can line those numbers up again, I get 32.7 minus 0.3, and that's ends up being, well, we don't normally see decimals on the top of the fraction, so I'll multiply top and bottom by 10. I've got 324 and 990. That simplifies down. The reality is that's a pain in the neck. It's much easier to look at it and say, hey, there's a pattern happening here. Let's look at it a different way. 0.6 repeater. Let's say we know what that is, but I'd go, hang on the top of the fraction I'm going to put what's recurring. That's 6. On the bottom of the fraction I'm going to put 9. Why 9? Well, there's one number recurring, so I'll put 1 9 on the bottom of the fraction. So it's 6 over 9, 2/3. Okay. 0.1 repeater would be 1 over 9. 0.2 repeater would be 2 over 9. 0.3 repeater would be 3 over 9, or 1/3, which of course now means 0.9 repeater is 1. Okay. 0.9 repeater is 1. 0.81 repeater then, using that same idea. Top of the fraction, I'll put 81. That's the number that's recurring. The bottom of the fraction, I put 99. There are 2 numbers recurring, so I put 2 9s down there. Not 18, but 2 9s, 99. There it is, and simplifies down. I can do that every single time. So if I had this one, 0.7134, and all the numbers are recurring, I'll go, well, hang on, I know what that is. That's 7,134 over 9,999. There are 4 numbers repeating, so I'll write 4 9s down. Does that simplify? Yes, it does. Well, what about this one then? How do I deal with this one? On the top goes 324. Why is it 324? I write down 327, but I subtract the number that's not recurring. I subtract the 3. So I get 324 on the top. Well, what do I put on the bottom? I put 990. Why? Well, there are 2 numbers recurring. So same as I did before, I'll put down 2 9. But I've got 3 numbers I'm playing with. I need to put another number down, so I put down a 0. Got to be at the end, because if I put it at the front, then I've still got 99. So it goes at the end. 990. There's the answer. 18 on 55. So if I had this, 0.1096 repeater, but just the 9 and 6 are repeating, now I know it's the 1086, right? 1096 minus the ones that are not repeating, 10, over 9900. 2 numbers are repeating, so I'll put down 2 9s. There are 4 numbers all up, so I'll put down 2 0s. If you don't believe me, put that in your calculator and you'll see that is indeed 10969696969696. Well, it depends how big your calculator screen is, I suppose. 969696969696. The wonderful thing about things going to infinity, 96969. I could just 96. We'd never finish. 96969696. Okay, so exercise 2A in our textbook. Also, I've grabbed some questions out of the old Cambridge as well.